Hello guys and welcome back. Today we're going to talk about Ohm's Law. What makes Ohm's Law what it is today? How to use it, how to do the calculations. And also we're going to talk about the Coulomb, the amp, the electron theory, the conventional current theory, the speed of current, the basic electrical circuits, the volt, the ohm, the watts, metric units, and Ohm's Law in general. Electricity has a standard set values. Before one can work with electricity, you must understand these values and know how to use them. Because the values of electricity measurements have been standardized, they are understood by everyone who uses them. For instance, carpenters use a standard system for measuring length, such as the inch, foot, meter, or centimeter. Imagine what a house would look like if it was constructed by two carpenters who used different lengths of measurement for an inch or foot. The same holds true for people who work with electricity. The standards of measurement must be the same for everyone. Meters should be calibrated to indicate the same quantity of current flow or voltage or resistance. A volt, an amp, or an ohm is the same everywhere in the world. In America, we normally say Coulomb, but the proper pronunciation in English is Coulomb. Is a quantity measurement for electrons. 1 Coulomb contains 6.25 times 10 to the power 18, or 6.25 quintillion electrons. That's 6.25 with 18 zeros to the right. To better understand the number of electrons contained in a Coulomb, think of comparing 1 second to 200 billion years. Since the Coulomb is a quantity measurement, it is similar to a quart, gallon, or liter. It takes a certain amount of liquid to equal a liter, just as it takes a certain amount of electrons to equal a Coulomb. The Coulomb is named for a French scientist who lived in the 1700s, named Charles Augustin Guy Coulomb. Coulomb experimented with electrostatic charges and developed a law dealing with the attraction and repulsion of these forces. The law known as Coulomb's law of electrostatic charges states that the force of electrostatic attraction or repulsion is directly proportional to the product of two charges and inversely proportional to the square of the distance between them. The number of electrons contained in the Coulomb was determined by the average charge of an electron. The amp or ampere is named after André Ampere, a scientist who lived from the late 1700s to the early 1800s. Ampere is most famous for his work dealing with electromagnetism, which will be discussed in a later chapter. The amp is defined as 1 coulomb per second. Notice that definition of an amp involves a quantity measurement, the coulomb, and a time measurement, a second. 1 amp of current flows through a wire when 1 coulomb flows past a point in 1 second. The amp is a measurement of the amount of electricity that is flowing through a circuit. For example, in a water system, it will be comparable to gallons per minute or gallons per second. The letter I, which stands for intensity of current, and the letter A, which stands for amp, are both used to represent current flow in algebraic formulas. The electron theory. There are actually 2 theories concerning current flow. One theory is known as the electron theory, and it states that since electrons are negative particles, current flows from the most negative point in the circuit to the most positive. The electron theory is more widely accepted as being correct. The conventional current theory, the second theory, known as the conventional current flow theory, is the older than the electron theory, as states that current flows from the most positive point to the most negative. Although it has been established almost to a certainty that the electron theory is correct, the conventional current theory is still widely used for several reasons. Most electronic circuits use the negative terminal as ground or common. When the negative terminal is used as ground, the positive terminal is considered to be above ground or hot. It is easier for most people to think of something flowing down rather than up, or from a point above ground to ground. An automobile's electrical system is a good example of this type of circuit. Most people consider the positive battery terminal to be the hot terminal. Many people who work in the electronics field prefer the conventional current flow theory because all the arrows of the semiconductor symbols point to the direction of the conventional current flow. If the electron flow theory is used, it must be assumed that current flows against the arrow. Another reason that many people prefer using the conventional current flow theory is that most electronic schematics are drawn in such a manner that it assumes current flows from the more positive to the more negative source. The positive voltage point is shown at the top of the schematic, and the negative ground is shown at the bottom. When tracing the flow of current through a circuit, most people find it easier to go from top to bottom than from bottom to top. Speed of current. To determine the speed of current flow through a wire, one must first establish what is exactly being measured. As stated previously, current is a flow of electrons through a conductive material. Assume for a moment that it is possible to remove a single electron from a wire and identify it by painting it red. If it were possible to observe the progress of the identified electron as it moves from atom to atom, it will be seen that a single electron moves rather slowly. It has been estimated that a single electron moves at a rate of about 3 inches per hour at 1 amp of current flow. Another factor that must be considered is whether the circuit is DC, AC, or radio waves. Radio waves move at approximately the speed of light, which is 186,000 miles per second, or 300,000 meters per second. The velocity of alternating current through a conductor is less than the speed of light because magnetic fields travel more slowly in materials, dielectrics, than they do through free air. The formula shown can be used to compute the speed or wavelength a signal travels through a conductor. Wavelength is the distance that current travels during one cycle of alternating current. L equals 984 V over F. L equals length in feet, V velocity factor, F frequency in megahertz. The velocity factor is determined by the type of conductor. In a direct current circuit, the impulse of electricity can appear to be faster than the speed of light. Assume for a moment a pipe has been filled with ping pong balls. If a ball is forced into the end of the pipe, the ball at the other end will be forced out. Each time a ball enters one end of the pipe, another ball is forced out of the other end. This principle is also true for electrons in a wire. There are billions of electrons in a wire. If an electron enters one end of the wire, another electron is forced out of the other end of the wire. Assume that a wire is long enough to be wound around the earth 10 times. If a power source and switch were connected at one end of the wire and a light at the other end, the light will turn on the moment the switch was closed. It will take light approximately 1.3 seconds to travel around the earth 10 times. Basic electrical circuits. A complete path must exist before current can flow through a circuit. A complete circuit is often referred to as a closed circuit because the power source, conductors, that note from a closed loop. Another type of circuit is the short circuit, which has very little or no resistance. It generally occurs when the conductors leading from and back to the power source become connected together. For example, a separate current path has been established that bypasses the load. Since the load is the device that limits the current flow, when it is bypassed, an excessive amount of current can flow. Short circuits generally cause a fuse to blow or a circuit breaker to open. If the circuit has not been protected by the fuse or circuit breaker, a short circuit can damage the equipment, melt wires, or start fires. Another type of circuit, one that is often confused with a short circuit, is a grounded circuit. Grounded circuits can also cause an excessive amount of current flow. They occur when a path other than the one intended is established to ground. Many circuits contain an extra conductor called the grounding conductor. A typical 120-volt appliance circuit will include the ungrounded or hot conductor, which is connected to a circuit breaker. The hot conductor supplies power to the load. The grounded conductor or neutral conductor provides the return path that completes this circuit back to the power source. The grounding conductor is generally connected to the case of the appliance to provide a low resistance path to ground. Although both the neutral and grounding conductors are grounded at the power source, the grounding conductor is not considered to be a circuit conductor because current will flow through the grounding conductor only when a circuit fault develops. In normal operation, current flows through the hot and neutral conductors only. The grounding conductor is used to help prevent a shock hazard in the event that the ungrounded or hot conductor comes in contact with the case or frame of the appliance. The volt. Voltage is defined as an electromotive force, or EMF. It is the force that pushes the electrons through a wire and is often referred to as electrical pressure. A volt is the amount of potential necessary to cause 1 coulomb to produce 1 joule of work. One thing to remember is that voltage cannot flow. Voltage in an electrical circuit is like pressure in a water system. To say what voltage flows through a circuit is like saying that pressure flows through a pipe. Pressure can push water through a pipe. Then it is correct to say that water flows through a pipe. But it is not correct to say that pressure flows through a pipe. The same is true for voltage. Voltage pushes current through a wire, but voltage cannot flow through a wire. Voltage is often thought of as potential to do something. For this reason, it is frequently referred to as potential, especially in older communications and service manuals. Voltage must be present before current can flow, just as pressure must be present before water can flow. A voltage or potential of 120 volts is present at a common wall outlet, but there is no flow until some devices connected in a complete circuit exists. The same is true in a water system. Pressure is present, but water cannot flow until the valve is open and a path is provided to a region of lower pressure. The letter E, which stands for EMF, or the letter V, which stands for volt, can be used to represent voltage in an algebraic formula. The ohm. An ohm is the unit of resistance to current flow. It was named after the German scientist George S. Ohm. The symbol used to represent an ohm or resistance is the Greek letter omega. The letter R, which stands for resistance, is used to represent ohms in an algebraic formula. An ohm is the amount of resistance that allows 1 amp of current to flow when the applied voltage is 1 volt. Without resistance, every electrical circuit would be a short circuit. All electrical nodes, such as heating elements, lamps, motors, transformers, and so on, are measured in ohms. Just as in the water system, a reducer can be used to control the flow of water, in an electrical circuit, a resistor can be used to control the flow of electrons. To understand the effect of resistance on an electrical circuit, imagine a person running along a beach. As long as a runner stays on the hard compact sand, he can easily run along the beach. Likewise, current can flow easily through a good conductive material, such as copper wire. Now imagine that same runner, wade down into the water until it is knee deep. He will no longer be able to run along the beach as easily as he could because of the resistance of the water. Now imagine that the runner wades out into the water until it is waist deep. His ability to run along the beach will be hindered to a greater extent because of the increased resistance of the water against his body. The same is true for resistance in an electric circuit. The higher the resistance, the greater the hindrance to current flow. Another fact an electrician should be aware of is that anytime current flows through a wire, heat is produced. That is why a wire becomes warm where current flows through it. The elements of an electric range becomes hot, and the filament on an incandescent lamp becomes extremely hot because of resistance. Another term similarly meaning to resistance is impedance. Impedance is the most often used in calculations for alternating current rather than direct current. The watt. Watt is a measure of the amount of power that is being used in a circuit. The watt was named in honor of the English scientist James Watt. In an algebraic formula, wattage is generally presented either by the letter P for power or letter W for watts. It is proportional to the amount of voltage and the amount of current flow. To understand watts, return to the example of the water system. Assume that a water pump has a pressure of 120 pounds per square inch, or psi. It causes a flow rate of 1 gallon per second. Now, assume that this water is used to drive a turbine. The turbine has a radius of 1 foot from the center shaft to the rim of the wheel. Since water weighs about 8.34 pounds per gallon, and it is being forced against the wheel at a pressure of 120 psi, the turbine will develop a torque of about 1,000 foot-pounds of torque. We can see that 120 times 8.34 times 1 equals 1,000.8 foot-pounds of pressure. If the pressure is increased to 240 psi, but the flow of water remains constant, the force against the wheel will double. 240 times 8.34 times 1 equals 2001.6 foot-pounds of torque. Notice that the amount of power developed by the turbine is determined by both the amount of pressure driving the water and the amount of the flow. The power of an electrical circuit is very similar. For example, a resistor is connected to a circuit with a voltage of 120 volts and a current flow of 1 amp through it. The heating element would produce 120 watts of heat. 120 times 1 equals 120 watts. If the voltage is increased to 240 volts, but the current remains constant, the element would produce 240 watts of heat. 240 times 1 equals 240. Ohm's law. If the voltage remains at 120 volts, but the current is increased to 2 amps, the heating element will again produce 240 watts. 120 times 2 equals 240 watts per Ohm's law. Notice that the amount of power used by the heating element is determined by the amount of current flow and the voltage driving it. The watt is not the only unit of power measure. Many years ago, James Watt decided that in order to sell his steam engines, he will have to rate their power in terms that the average person could understand. He decided to compare his steam engines to the horses he hoped his engines would replace. After experimenting, Watt Watt found that the average horse working at a steady rate could do 550 foot-pounds of work per second. A foot-pound is the amount of force it requires to raise 1 pound weight 1 foot. Take 44. Another measure of energy frequently used in the English system of measure is the BTU, British Thermal Unit. A BTU is defined as the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. In the metric system, the calorie is used instead of the BTU to measure heat. A calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. The joule is the metric equivalent of the watt. A joule is defined as 1 Newton per meter. A Newton is a force of 100,000 dynes, or about 3.5 ounces. And a meter is about 39 inches. The joule can also be expressed as the amount of work done by 1 coulomb flowing through a potential of 1 volt, or as the amount of work done by 1 watt for 1 second. Ohm's law. In its simplest form, Ohm's law states that it takes 1 volt to push 1 amp through 1 ohm. Ohms discovered that all electrical quantities are proportional to each other and can therefore be expressed as mathematical formulas. He found if the resistance of a circuit remained constant and the voltage increased, there was a corresponding proportional increase of current. Similarly, if the resistance remained constant and the voltage decreased, there would be a proportional decrease of current. He also found that if the voltage remained constant and the resistance increased, there would be a decrease of current. And if the voltage remained constant and the resistance decreased, there will be an increase of current. This finding led Ohm to the conclusion that in a DC circuit, the current is directly proportional to the voltage and inversely proportional to the resistance. Since Ohm's law is a statement of proportion, it can be expressed as an algebraic formula when standard values such as the volt, amp, and ohm are used. 3 of the most basic formulas are E equals I times R, I equals E over R, and R equals E over I. E stands for EMF or voltage. I stands for intensity of current or amps. And R stands for resistance. The first formula states that the voltage can be found if the current and resistance are known. Voltage is equal to amps multiplied by ohms. For example, Assume a circuit has a resistance of 50 ohms and a current flow through it of 2 amps. The voltage connected to this circuit is 100 volts. E equals I times R. Therefore, E equals 2 times 50. Therefore, E equals 100. The second formula states that the current can be found if the voltage and resistance are known. In the example below, 120 volts are connected to a resistance of 30 ohms. The amount of current flow will be 4 amps. The metric unit. Metric units of measurement are used in the electrical fields just as they are in most scientific fields. A special type of metric notation known as the engineering notation is used in the electrical measurements. Engineering notations is the same as any other metric measure except that engineering notations is in the step of 1000 instead of 10. The first step above the base unit is deca, which means 10. The second unit is hecto, which means 100. And the third unit is kilo, which means 1,000. The first unit below the base unit is deci, which means 1/10. The second unit is centi, which means 1/100th. And the third is milli, which means 1/1000th. So let's get started doing some Ohm's law calculations.